Yeah.
Thank you. So we're going to talk about, we're into the area of molecular interaction, and I'm going to introduce a new technology called SwitchSense. I've got a video to show how it all works. So these measurements are done on a small microfluidic chip, and on this chip there's 24 small gold electrodes. On these gold electrodes we're applying a positive and a negative voltage, 10,000 times a second. Why do we want to do this? It's to move these DNA nanolevers. So these are small DNA structures that are tethered into the gold, and as we apply this positive-negative voltage, they're attracted and repelled. We can see this movement happening, this is the nub of it all, because on one of the strands of DNA we've got a fluorescent tag. As the lever lies flat in the gold, the lights go out. As it stands back up, the lights come on again. And so our measurement is actually one of fluorescence, and we're tracking the movement in real time of these levers as you stand up and sit down. How do you use this in a kinetic experiment, for instance? On the other complementary DNA strand, we've got a ligand. You wash through your analyte, and if the two interact and stay together, the movement of that DNA lever is actually slowed down. So the main effect here is one of hydrodynamic friction, so it's like pushing a large beach ball through water versus a small ball. And on the right, if you have a naked DNA nanolever, that moves quicker than the one on the left. So our main measurement is one of speed at which these levers lie down and stand up. And this is how we see in real-time interactions. The interesting part of this technology is its flexibility. And here we have some of the different structures we can play with, from kind of classical simple kinetics, antibodies and proteins interacting. The structures can be made of DNA or RNA or PNA, and we can do simple and interesting SNP analysis mismatches. Does DNA stick to other bits of DNA? The area of proteins interacting with DNA is obviously very easy in this process. We can simply change the sequence of the DNA, and we've done interesting work like polymerases, so we can see polymerases bind, move, expand, basically doing PCRs off these. Small molecules, one of the interesting areas is that the fact that we can size the molecules very accurately. So we can see, for instance, if a small molecule interacts, does the protein open up, does it close, does it compact, does it change in charge? Also, the chip is heated up between 4 and 75 degrees, so we can melt the protein. So we can see the thermal stability of the protein following small molecule interaction. We have some rather more esoteric designs of the structures. This is called a slingshot. This is made of DNA, and the blue spacer bar at the top we can make to various lengths and orientations. And that gets us into the area of avidity measurements. So molecules that have more than one binding site, and we can measure the K-offs of one arm versus the other arm and things like this. As I said, we can do sizing. We can look at things getting bigger or smaller. We group our data output into two kind of categories. One is interaction, so kinetics and avidity. We can run these systems in parallel under various conditions. And the output in this kind of area of biophysical analysis, we can look at size, we can look at aggregation of various things as they grow on, we can look at conformational change, unfoldings of proteins, compaction. As I say, with the heating aspects, we get into the mysterious world of thermodynamics. And we can look at, for instance, post-translational modifications. What impact does that have on the protein size and charge and structure? Lots of fun things to try. If you would like to have a chat about trying this out, I've got a booth, and the company's based in Munich. And thank you very much.
Thank you. Well, fascinating technology, new technology. Thanks all the speakers in the morning session for interesting and great presentations. I'll wish you a nice lunch, and I hope you're going to be